Oh, hey, hi. I didn't even see you there. Kind of creepy how you were right behind me and I didn't even notice. That was weird. I'm just chilling out. What are you doing? What? You want to talk calculus? Sure. It's your lucky day because I'm just about to do integration by parts. How awesome is that? Did you like that intro? Normally I'm like, hey, welcome to Unit 6, Day 4. And I figured I'd change it up a little bit after doing like 50 Algebra 2 videos and now some calculus videos. Um, I was going to go with the Mr. Rogers thing. It's a beautiful day in the calculus class. We're about to do some stuff, so you better learn to pass. Can't you integrate? Hi, friend. We're going to do calculus by parts. But I figured that was a little too creepy on my end. So let's just start. Integration by parts. I love it. Boom. First, let's talk about Mr. Richard Dickey Lippitt, Florida Shrine Association president, 1967. What I typically do in class is I tell an elaborate story, completely made up, about Mr. Richard Dickey Lippitt here. I say that he was a beloved president. He was in a community where everybody thought he was a great guy, and it turned out he was like the enforcer for the mob, and like someone in his neighborhood like gambled and lost a lot of money, and he had to go like break their hands with a sledgehammer, and he got arrested, and in jail he stabbed someone, and I make it really like the kids are like, what? Really? I can't believe it. I'm like, yeah, Lippitt. Everybody in jail used to be like, hey, here comes Lippitt. You know, here comes Dickey Lippitt. But then I say, well, that was really a made up story. The whole reason I mention this guy's name is his last name is critical. And it's not because he had anything to do with math. There's a process. It stands for an acronym for a process that we're going to use. And when I tell such a crazy, outlandish story, people tend to remember the word Lippitt more. And I swear, I looked up Richard Lippitt or just Lippitt, and this guy picture came up in Google, so that's why I use it. Okay? He is an actual person. I don't know anything about him besides the fact that he was a Florida Shrine Association president in 1967. That's all I know about him. Okay? So let's move forward. Integration by parts. Good news, you booze there. You have this equation, and with much of calculus, if this is the first time you're seeing it, I needed some coffee. I'm sorry. I got this new Oreo creamer, and now I'm doing the no carbs thing, so I really can't have it. So I can have like a little teaspoon. It's killing me. Anyways, much like most of calculus, you see an equation and you're like, what the heck is that? Don't worry, I'm going to explain it. Just make sure you write it down. My integration of u with respect to dv equals u times v minus the integration of v du. All right. So what does that mean? Well, I don't know. Let's talk about it. There are two functions in your integrand. Remember, the integrand is this thing right here. It's my expression that I'm integrating, the integrand. There are two functions. U is one of your functions, and dv is another function, okay? And we kind of separate them into parts, and we do this process called integration by parts. All right? So we have this first example. Example 1, x cosine of x dx. All right? Now, if someone were to look at this and automatically think u sub, I'm going to do u sub. Okay, well, let's make u my x. So du would equal 1 dx. So for this dx, I get du. I'm going to put u here. I still have nothing to do with this x. That's why u sub won't work. If I can't get rid of the variables I need to get rid of in order to integrate, I cannot do u sub. And this is where integration by parts comes into play. All right? Now, the million-dollar question is, Lippitt asks, my friend Richard Dickey Lippitt, he asked this, which one's the u and which one's the dv? I said we have two functions, right? I see two functions here. I see an x, that's function 1, and I see a cosine of x, that's function 2. So which one is which? Gaha. Gaha. just tried to lip it. Okay, Richard Dickey Lippitt, his last name, it's an acronym. I think that's what it's called. It's probably not synonym, homonym, acronym. I don't know. I'm horrible with words. I'm good with numbers, though. Great with numbers, just horrible with words. Okay, the priority for my U function. Okay, let's go back. Okay, the priority for my U. So which one is going to be my U versus which one's going to be my DV? All right, and there is a priority to which we choose these things. If you have a log, that is the first, and obviously here's top priority, and then they go down this way. Okay, logs should be assigned the U first. If there are no logs, logs, obviously that's log. That's also natural log. Inverse trig would be next. If I don't have any logs, it's inverse trig, which is sine -1 of x or whatever of U I should write, or cosine -1 or tan -1. If there are no logs or inverse trig, polynomials should be next. It could be anything like x cubed plus x squared. It could be x. It could be 3x to the 5th minus 2. Whatever. I think you know what a polynomial is at this point. If there are no lip, no logs, inverse trigs, or polynomials, the next one that should get the U assignment is my exponentials. Anything with an exponent that's a variable. E to the x, that's an exponential. 2 to the x, that's an exponential. And then last but not least, on the bottom of my lipid, of my U function substitution, is just classic trig. Sine, cosine, tangent. All right? So this name lipid is important. Well, it's not the name that's important. It's the word that we use. It happens to be this guy's last name, who was a big mob king. And I'm just kidding. But the story is definitely awesome. If you were ever in my class, and I just make it up on the fly. I have kids. I hold them in the palm of my hands. And then I'm like, I show them this. I'm like, wow, that's cool. Really? And I'm like, you know that story? That was just made up. And they're all devastated. It's a fantastic. There's little things being a teacher that just make me feel good about teaching. Lying to my students is one of them. I'm just teasing. Let's go. Okay, so now we know lipid. That's huge. So as I look here, I have a polynomial, and then I have trig. Polynomial is higher than trig on my lipid scale. So my polynomial is going to be my U. So I have U, I'm going to assign that x. Du is just 1 dx, okay? My other function, the one that is not the U, is the dv. Okay, it is not the v, it's the dv. That's cosine of x dx. Okay, so actually I'm going to just take it as cosine of x dx. All right, so what's my v? Be careful because now I have to integrate. So when I have my u, I take the derivative. And when I have the dv, I have to integrate. So be careful. One of the huge, biggest mistakes in this process is when kids start to go fast and they mix up derivatives and integrals, the process. Like someone might say, okay, the derivative of cosine is negative sine, which it is, and they'll put it here. That's wrong because I don't want the derivative of cosine. I want the integration of cosine. I have the derivative. What do I take the derivative of that gives me cosine? Well, that's sine. When I integrate cosine, I get sine. Okay? Now I have these 4 bits of information, and they're all going to come into play, meaning u times v. U times v. Okay, that's the first thing I write. And I'll write this out. U, v minus the integration of v du. So my u is x. My v is sine of x. I literally did this. Minus the integration of, highlighter, I love you. Okay, v du. V, wow, that got nasty fast. V du. All right, so v, which is sine of x, du, which is just dx. Okay, now this becomes manageable to integrate. Here, it was not manageable at all. We were stuck. We did this integration by parts, flip it, and we end up with something that's so much more manageable to integrate. This stays the same and just comes along for the ride. X sine of x minus, okay, the integration of sine of x. What do I take the derivative of that gives me sine? Well, cosine gives me negative sine. So it must be negative cosine of x. Okay, don't forget, this is an indefinite integral. I do not have any bounds. I'm not putting zeros there. I'm circling. There are no bounds, so I need to put a plus c. All right? And now I just clean this up. I distribute my negative. So I have x sine of x plus cosine of x. And even though I distribute that, my constant I always make plus c. But isn't it like minus c? What if I'm subtracting a negative 3? Doesn't that turn to a plus? Yeah, I'll be okay. A plus 3? It does. Okay? So we always just leave that constant as a plus. It's just a habit in math, okay? But what if it's negative? Okay, well, we would add a negative 3. It would still be minus. Okay, but we still use a plus for our constant. Okay, we always use that plus. And that's our answer right here. Not too horrible, was it? I didn't think it was bad. Lippet likes it. Look it. He's smiling. Yay! It's Y-A. Why? I think, again, I'm horrible with words. But he likes it. Dickie likes it. If you feel confident in number 2, try it. Pause the video because I am about to wreck this problem. Example number 2. I'm going to use Lippet. I see a polynomial, P, and I see a log. What comes first? Log definitely comes before polynomial. So the log, in this case the natural log, is my u, natural log of x, which means du is 1 over x dx. Okay. That means my polynomial, my x, is my dv. That's x dx, which means v, if I integrate that, it's x squared over 2. All right. Now I just fill in this part. My equation, okay, equals this part. And I just put in right here my u's, v's, and my du. Notice the dv doesn't even come into play. We assign dv, but back here, we don't even use it. Okay, that just helps us, knowing the dv helps us come up with the v when we integrate it. And that's the important part. Okay, so let's take a look at this. I'll get in the habit of rewriting this. uv minus the integration of v du. So u, v, let's multiply them together. I have the ln of x times x squared over 2 minus the integration of v, all right, du. So it's x squared over 2 times 1 over x dx. All right, all right, all right. It's a little sloppy. Let's clean some of this up first. This integrand I'm going to simplify, okay? This x can cancel with one of these. All right, good, good, it's good. And like right here, I'm going to write this in a way we normally see it. This would come first. I'm going to just put x squared over 2 ln of x minus the integration of x over 2 dx. In fact, this integration I'm going to write differently as well. And I'm writing all these steps, which you don't really have to write. But I would like to show you where my mind is coming from. Because once you enter this brain, oh, there ain't no going back. X squared over 2 ln of x minus the integration. That's like saying 1/2 x dx. And any constant, we can just pull that out. So ultimately, and I hate rewriting this all this time, but again, If this were a problem and homework and a test, you wouldn't have to show every single step. I'm just showing you every single step because I know someone is going to say, wait, how did that happen? So I'm showing you. So we have x squared over 2 ln of x minus 1/2 the integration of x dx. Well, we already did the integration of x. So it's x squared over 2 ln of x minus 1/2 times the integration. Okay, now I'm just going to integrate this part. That's x squared over 2 plus c. And now let's just clean this up. Let's just clean this up. Okay, so equals x squared over 2 ln of x. Okay, if I multiply it, minus x squared over 4 plus c. Fantastic. Look at you. And I rewrote every single step along the way. Okay, I rewrote every single step along the way. Like, I could have literally, if I'm good at this and I know what I'm doing, I could go from this step before I canceled everything out in green. I could have went right to here. Okay, I could have really omitted all these steps here. Okay, why did I show them to you? Because I wanted you to see where they came from in my mind. All righty, children. X squared e to the x. Let's do it. According to Lippitt, this is a polynomial. This is an exponential. And in Lippitt, polynomials come before exponentials. So my u is going to be x squared. Du equals 2x dx. That means my exponential is my dv, which is ex d to the x. And if I integrate that, it's still e to the x. Okay? And let's start using this right here. U times v. It is x squared, which is my u, times my v, which is e to the x, minus the integration of v, which is e to the x, du. Du is 2x dx. All right. Well, I cannot integrate e to the x to x, even with u sub. I mean, I can, but not using u sub. That's not a clean one. I can't just integrate it. I can't use u sub because if I say x is u, du would be just 1 dx. So it would get rid of this dx, but I would still have this variable. And I can't get rid of it to integrate, which means, guess what I got to do? I got to integrate this right here by parts. If I wanted to, I could take this 2 and pull that out, but let's just do everything as it is, okay? I've got to integrate this integral by parts, just like I did here, a second time. Again, polynomials take precedent over exponentials. So my u is 2x. My du is 2 dx, which makes my dv e to the x dx, and my v is e to the x. So this is going to be fun and interesting. So if you're comfortable with doing this process once, that's cool. You're just doing the process a second time. Big deal. Who cares? But it's long. It's a lot to write. Stop whining with your mamby-pamby anti-math spewing. Just do it. The only way to get something done is to just do it, okay? In fact, the guy that came up with the logo for Nike was probably a dad who just got tired of yelling at his children to do chores. Just do it. Just do it. And then he was like, oh my God, it's a brilliant marketing scheme. And look at him today. Of course, I made that up. I don't know. Anyways, here we go. This is going to come along for the ride. X squared e to the x minus. I've got to use my integration by parts just for this process I'm about to do right now. Okay? It is u times v. So now it is 2x e to the x minus the integration of v du. That is 2 dx. I am absolutely Going to take this constant out. It becomes a 2 and goes bye-bye. Now that integral is so easy to integrate. What's the integration of e to the x? It is just e to the x, and I still have my plus c. I just integrated this right here. So I still have a minus 2 out in front of it to multiply. I have my 2x e to the x out in front of here. And in front of that, join us for the ride, my friends. X squared e to the x minus. So let's just clean this up. Let's clean this up, shall we? There, you did integration by parts twice, and you're done. So we have x squared e to the x. This applies to this too, and I've got to apply it to this too. Or if I want to work inside out, okay, let's do it that way just to prevent confusion. Let's distribute this to here. So I got negative 2 e to the x. A negative 2 times c is still going to be plus c. That takes this place. Now I got to distribute this negative sign here, here, and here. So I've got minus 2x e to the x. A minus times a minus is plus 2 e to the x. And it doesn't matter here. I still always put plus c. Brilliant. I love it. I love it. All right, let's move on. Now, what we have here, this is called solving for the unknown integral. This works, okay, now pay attention. This works when both of my factors, my u and my dv, my u would integrate and my dv would differentiate, or excuse me, yeah, I'll be okay. I'm crazy, dudes. My dv would integrate, because that's the one you got to take the integral of. And my u would differentiate forever, forever, forever. It would never stop. You would constantly do integration by parts forever. Okay, let me go back to the previous problem. You see how I had to do this a second time? Here's the first time. Then here's the second time, and then after the second time, it worked out. If both of these, you notice when I took the derivative of u, it went to 2x. Then I have 2x, take the derivative, it goes to 2. Okay, that it goes away, the variable goes away. If I took the derivative of 2, it would become 0 if I had to do it a third time, needed to. Okay, but my e to the x, you notice, just kept going forever, didn't it? All right, so let's go back here. Solving for the unknown, they both go forever, meaning I want to do it 2 times, 3 times, 4 times I want to do this process. I would just go on forever. So there's a way that we can get by that, okay? And this is going to be a lot of writing, so follow. Okay, follow it. We're still using Lipit. We're still going to do this thing by parts, all right? But when we have this situation, there is going to end up a certain part where there should a light bulb should go off, okay? And let me point that out when we get there. All right, Lipit tells me, well, this is trig. This is definitely last. This is exponential. E comes before t, so my e is my u, if that makes sense. U, e to the x. Oh, I love taking the integral and derivative of e to the x because it's just e to the x. That means my dv is cosine of x, dx. And if I integrate that, I would get sine of x. Let's start this process out, okay? We still need to do this integration by parts. That's not going away, okay, in this process. So I have u times v, e to the x, sine of x, minus the integration of, that's a v, children, v du. So it's sine of x, e to the x, dx. All right. Now keep in mind, what are we solving for? This actually equals, we're solving for this. So what I'm doing, this answer on the left side is supposed to equal the integration of e to the x cosine of x dx, okay? And I want you to write that to the side right now because this is going to help us with the light bulb that goes off, all right? So at this point, I should realize, oh, okay, well, I can't integrate this part easily, so I'm going to have to do integration by parts a second time. So let's go ahead and do that. Well, I have trig, and I have exponential, so my exponential is going to be my u. U equals e to the x. I should probably write the x in the exponent position. And du equals e to the x dx. Love it. My dv is sine of x. And my integration of that is the negation of the cosine of x. And sine of x should have a dx next to it. So let's go ahead and apply that now. Okay, comes along for the ride. All right, I have e to the x sine of x minus this is what I'm doing the integration by parts for the second time right here. Okay, so it is u times v. So it is, okay, a negative times a positive. It's a negative e to the x cosine of x. When I subtract the negative, that turns positive. Minus the integration of v du. Okay, negative. All right, cosine of x e to the x dx. So let's just do this. Let's okay, this negative, let's pop it out. It's like a -1. So let's rewrite this. Okay, so I have e to the x sine of x plus e to the x cosine of x plus the integration of, we'll write this e to the x cosine of x dx. In multiplication, order does not matter. Okay, and what does it equal? Let's not forget what we're solving for. This whole process, whatever answer we get, is supposed to equal the integration of e to the x cosine of x dx. This right here is where your light bulb should go off. Bing! Why should that have? Oh, maybe we can even do this. That would be nice. Bing! Look at us go. The light went off right here. What is so special about this? Let me tell you. What I'm trying to solve for has suddenly reappeared in the process of trying to solve for it. I have the same exact thing. So what I'm going to do is I'm going to treat this like it's a variable. Okay? You see how I have it on the left side of the equation and I have it on the right side of the equation? This is solving for the unknown integral. And this is the part that you need to get to. Whenever both of these integrate forever and differentiate forever, this will always happen. It should. I'm going to subtract the integral of e to the x cosine of x dx from both sides. Okay, wait. Boo-boo somewhere. Boo-boo somewhere. Let me figure this out. Okay, okay, good. Found it. You see this plus sign I'm getting rid of right here? Sine of x. It was minus the negation of e to the x, right? Which means not only do I have to flip this, I need to flip this too, because I'm subtracting, look right up here. I'm subtracting this whole thing, including the uv and the integral that comes from it. So I'm subtracting this whole thing. So I got to flip the sign here, all right? Which means when I negate this negative, it will become a positive. But now I got to negate whatever sign comes here, okay? You see how I put, and I'm going to show this to you one more time. I negated this and made it positive, right? I've got to negate it again to flip it back to negative. So cosine of x minus the integration all right? Which means instead of subtracting my integration from both sides, I'm adding my integration to both sides. Uh-huh. 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 So I'm going to add the integration, e to the x cosine of x dx. And I tell you what, when you go fast, and I'm not immune to them myself, I make mistakes every once in a while. The thing is, to be able to go back and see it and find it, that's where mastery comes from. Everybody made mistakes. Einstein made mistakes. In fact, one of my favorite quotes from Einstein was this: it's not that I'm smarter than everybody else. It's just that I stick with the problem longer than most people do to solve it. Most people give up. I don't. And, you know, being a math teacher, that's got to be your mantra. That's got to be in your arsenal somewhere. All right, back to here. This goes bye-bye. I now have e to the x sine of x plus e to the x cosine of x on the left side equals one integration plus another integration gives me two integrals of e to the x cosine of x dx. Well, if I'm solving for this, I should probably divide both sides by 2. And that's your answer right there, except we're missing one thing. And this isn't a mistake. This is just, oh, by the way, when I solve for my integration of e to the x cosine of x dx, it equals e to the x sine of x plus e to the x cosine of x all over 2. Don't forget, this is not a definite integral. It's an indefinite integral. I told you there was going to be a lot of writing. I did not disappoint, and I did not lie. So that's crazy. When they integrate and differentiate forever, that's when you're going to have to do this thing where what you're trying to solve for is going to pop back up somewhere in your equation. Okay? And it happened right here. All right? Purple. And it happened right here. I'm solving for this, and it popped right back up right here. All right? And if that's the case, you just solve for it like it's a variable because that's what I'm solving for. And we did, and wow, that was craziness. All right. Now, many of you are like, oh, this is a lot of work. At least many of my students do. And they always ask me, is there some sort of shortcut here that we can use? Now, for the problem we just did, the one where we are integrating for the unknown, right? Where this problem here, for the unknown integral, there's no shortcut here. For these other ones, there were shortcuts. Okay, there is a shortcut. And I'll show you how to figure it out. All right? When your u can differentiate to 0, like if I look at something and say, oh, if I keep on integrating this, I will eventually get a constant, then a 0. And your dv, okay, integrates repeatedly, means forever. Like e to the x will just integrate, become e to the x. Will just integrate, become e to the x. Will just integrate and become e to the x. Okay, you can use tabular integration. Okay, so much simpler. Okay, keep in mind, one you take the derivative of and it would eventually go to 0. The other one you integrate and it would just keep on integrating forever. It would cycle through. Trigonometry does that. Okay, cosine, sine, whatever, and e to the x. So big things here are sine, cosine, and e to the x. Integrate forever. Those are some of the big ones. Okay, differentiates to 0 like any sort of polynomial. X squared becomes 2x if I take the derivative, which becomes 2, which eventually becomes 0. Okay, so that's what I'm looking for. Let's try this. Boom. Do you remember exercise 3? We integrated this using parts. And this was our answer. Okay, that's the answer we came up with. So let's take a look at this. If I can catch that my u, which is the polynomial, I'm going to take the derivative of it, and it should go to 0. Okay? So this is my x squared. And then I should also realize that, oh, by the way, my dv I integrate. Don't take the derivative of both. Don't take the integral of both. Remember, my u, I take the derivative of. Okay? My dv, which is e to the x, I take the integration of. If you want to call it e to the x dx, go nuts. And I start this out here. I create this tab. It's almost like a table of coordinates. And look what I got. On the left side, I start with x squared. What's the derivative of x squared? It's 2x. What's the derivative of 2x? She's a 2. And the derivative of 2 is 0. There we go. I can take the derivative, and it will go to 0. I'm sure integration is not going to be a surprise to you at this point. The integration of e to the x, e to the x. Integration of e to the x, e to the x. The integration of e to the x, oh my God, it's e to the x. Yeah, sarcasm. Now, you attach these, you connect these diagonally. These two are going to become my first term. I multiply them. These next two will become the next term. I just write them side by side, or I multiply them. These next two here become my final term. When I'm done here, that's it, final term. One thing, and this is very important, you can't forget, you start by putting a plus, then a minus, and you just rotate the signs. Meaning, I have a positive x squared times my e to the x. I have a negative 2x times my e to the x. A positive 2 times e to the x, and so forth. So when I write this out, my first term, x squared e to the x. My next term, minus 2x e to the x. My last term, plus 2 e to the x. And of course, this is an indefinite, so I always put plus c. That's exactly what we came up with. And that, to me, is a million times easier. It is a shortcut for integration by parts if your derivative goes to 0 and your integration will go forever. Okay? Let's try one more here. You want to pause it and do it? Go ahead. I'm about to rip it up. This is my x cubed. It's a polynomial. That comes before trig. So this is my u. This is my dv. I have x cubed. It becomes 3x squared, becomes 6x, becomes 6, becomes 0. Derivative. Sine of x, be careful here. Integrate. Negative cosine of x. Integrate. Negative sine of x. Integrate. Cosine of x. Integrate. Sine of x. All right? And let's not forget, plus, minus, plus, minus, plus. Now let's write this diagonally. A positive times a negative would give me a negative x cubed cosine of x. A negative times a negative would give me a positive 3x squared sine of x. Positive times a positive would give me plus 6x cosine of x. Oh, I hate when I run out of space. Group and make this smaller. Sorry, that's bad. The next one, and the last one, negative times a positive is minus 6 sine of x. Let's not forget, this is an indefinite integration, so I put a plus c. And there you go. That is fantastic. That is fantastic. It's a negative, a positive, a negative. Negative, positive, positive. Yeah, okay, great. You guys are smart. All right, I will hopefully see you for another video coming up soon. Next time, don't like be creepy and creep up on me like that. That kind of freaked me out a little bit. It did. It did. See ya.